Hello, YouTube. I'm Will. I'm one of the mentors for Technomancers, Team 1758 for First Robotics. I'm here with.
Hey guys, my name's Zach. I'm the senior programming captain for FRC Team 1758.
Yep, and he's done a great job with it. What we were gonna do today?
So today we're going to be covering the robot code for our season this year, 2017.
And I guess as you see on the screen, it's going to be that. So what was the first thing you wanted to cover about the code?
So in a previous video you were talking about entry points. So I was wondering specifically where might be the entry point for robot code.
Alright, so with the previous tutorial, with the entry point, we only had that main method inside of the class that was our entry point. Inside of iterative robots for robotics, which is the main one that everyone uses, there are others, but don't quote me on them as I don't know them. There are quite a few steps, should I say, in the execution of the code. The first of which is actually initializing the robot, and that's what this first method is, the public init. This is what actually gets called once whenever code is executed. So you connect to the driver station, this gets called once, this stands up everything, we create a new controllers, set up our commands, get encoders, calibrating stuff, all that fun mess set here. Then we have what's called a periodic step, which is what actually loops through and actually does things. What we're doing is, no matter which periodic we're in, we're updating a smart dashboard so that we can get values out of it. This is the smart dashboard command that we're actually using to update our values. Autonomous init is called once whenever you enable autonomous. Not when you click autonomous, but when you actually enable it, it gets called once, and then it goes through and calls the autonomous periodic, which gets called multiple times within autonomous for 15 seconds. Then we have the teleop init, which gets called once when teleop is enabled, and then it goes through the teleop periodic and calls that multiple times throughout teleop. And that's why there's multiple entry points. It depends on the stage in which the robot is in to actually which part of the code is actually executed.
Okay. So as far as how code actually interacts with the robot, where would be considered like the main computer brains of the robot?
Alright, so physically in the real world, the brains of the robot is the Robo-Rio. This is what actually connects all the motors, the drive, the speed controllers, your encoders, your cameras, your sensors, all of that is controlled by the Robo-Rio. You could have an Arduino controlling your sensors and a Raspberry Pi controlling the sensors, but ideally, everything in itself is controlled by the Robo-Rio in some shape or form, whether it's reading from sensors or moving motors. Inside the code, we can kind of see the same thing, because our code has to call the encoders or call the motors to actually move a certain speed at a certain time, depending on certain conditions. So, the Robo-Rio, I would say, is the brains of the computer. Or brains of the robot.
Okay, thanks. So you were talking about how in the code we actually have to call encoders and motors. Could you elaborate more on how the code actually interacts with those things?
Yes, so one of the first places I would go to is a robot map. This is what maps everything, so the different ports, right? We have a right front motor, right back motor, left front motor, left back motor. These are all of the different ports that the Robo-Rio sees these speed controllers as. These speed controllers we're using are Talons in a CAN bus system. Also note, I'm going to go to the part of the code that has encoders codes per revolution. Notice how that's a pretty high number. I'll cover that in a second. But where this is actually called and used is within drivetrain itself. You can think of it as a subsystem. A subsystem is a part of the robot that is completely separate from the rest of the robot. For example, this year as 2017 SeamWorks, you would have a part of the robot that did the gear, the unloading, reloading of the gear. You would have a subsystem to deal with, let's say, just the cameras. Or we would have a part of this subsystem, or another subsystem that had to deal with picking up balls. And a separate one to do throwing of balls, because that's two different actions, so I would keep those separately personally. But depending on your robot, they may be the same thing. But let's stick with drivetrain, because every robot has a drive system of some sort. So let's go over the motors. We have, you can see in the top 4 places, we have our different CAN talons, which are our speed controllers in a CAN bus situation. And we're not initializing, but creating an instance of those variables first. Then we go through the constructor, where actually the drivetrain is created, and we set the motors up using that robot map values, those port numbers. So we say, hey, I want a new CAN talon on this port and save it to this variable. We then use those motors to set up a drivetrain. The TM, I assume, is Technomancer's drive. Probably could mean something else, but that's what I think of it whenever it's called TM drive. Then we use that TM drive, which actually is the brains of everything. That's the actual thing that's controlling the motors, whether this motor should go forward, this motor should go back, or whether these two motors should go in opposite directions, stuff like that. That is the brains of it. But then we kind of overlay on top of it, and we create a mechanism drive Cartesian, which is what tells a robot to, in certain situations, to do certain things. Kind of broad, but a mechanism drive moves forward, back, turn left, turn right, slide left, slide right, even though I did that backwards. But we pass in all those values into this method, and then the TM drive figures out, okay, well, to do what the operator wants us to do, these wheel needs to turn in these rotations. Same with tank drive, except tank drive can't slide left and slide right, it can only turn and go forward and back.
Okay.
Yeah.
So you quickly mentioned encoders and the encoder codes per revolution. So could you let me understand exactly what are encoders?
Alright. Encoders is a way to measure the number of revolutions a motor has gone. Or where we have ours is inside of the gear inside of the gearbox. We have our encoders. And you noticed it was like 1024. That's 1024 pulses per revolution, meaning this thing sends a pulse to the RoboRio 1024 times in one revolution of that wheel. If our wheel is 6 inches in diameter, that means we have 6 pi distance covered whenever we go forward 1024 pulses. That's kind of how you can relate to it in the real world, so that in the real world I need to move 18 inches or so. Roughly 18 inches, just doing math real quick, would put me at 1 revolution, and I could say stop after that. And you can use that for a conversion type thing. The encoders can also tell you speed, because you also have a little bit of relation in time there, so you can figure out how fast it's rotating as well. But the reason is 1024 pulses is so that you have a little bit finer control. You don't have to say, hey, have I hit 1 revolution yet? Oh, no, I've hit 1024th of a rotation.
Okay.
But yeah, so to use that value, what we do is we configure our encoders here, and to do that, we just set each motor to use that 1024 whenever we configure it. If we ever need to reset it, like, let's say we're running a command like, say, let's go forward 24 inches. Well, we want to make sure the base for all of our motors are 0 before we say go 24 inches. So we reset them to 0, and then it counts up to 20, or whatever 24 inches to rotations per evolution is, or pulses per evolution is. So that covers the basics of it. You can get the velocity out of them, as I said, and you can get the position of them. So.
Okay. So back in the main robot.java, I noticed that there were a lot of like commands being called and command base. So could you actually talk about what command base is?
All right. Command base is a class that is extended by all commands. We use a command-based robot, so a robot has different commands that it can run. Drive with joystick is a popular one because we need to be able to drive with it whenever we're in teleop. But we also have commands like approach peg and turn left, turn right. wait till, stuff like that. Very simple commands. If you can break these commands up into small sections, then you can combine them together in command groups. That's probably a little bit more of an advanced topic, but to get back to what a command base is, it is the base that all commands extend from. What it includes is it includes like it includes an object of drivetrain, vision, gear, compressing, and rope. That was for our robot. We had no ball pickup or no throwing this year. But that's what our command base has. Then, whenever we initialize a new instance of command base, we actually tell it to, hey, create a new instance of drivetrain, create a new instance of vision, and save them into these static variables. That way, whenever a command is extended from it, we can say, hey, you require this subsystem, make sure it's not already in use, and then use it. A good example, as I said earlier, was probably drive with joystick. So, let's see, where is drive with joystick? It is somewhere. I'm probably blind. Alphabetical order. There we are. Alright, so if I want to drive with joystick, there's a couple different things. The one required thing is this isFinished method. That is required by anything that extends a command, which command base extends. You'll notice that this extends command base. Also, when we whenever we create a constructor for it, we tell the system, hey, this requires the drivetrain. So make sure the drivetrain is not being used by something else. Then we initialize it with default values, like first iterations, making sure nothing's getting... Just make sure everything's in a refresh state whenever we want to start this. This gets called once whenever we call command.start. This is called once. Then we have this execute, which is the loop of the command. This is what actually gets run multiple times. You'll notice that if I want something ran once, I could do it either in the initialized state or inside of the execute state using a boolean saying is first iteration. Then what we're doing is we're getting certain button values back, doing certain things based on those button values. The main thing that we're doing is taking our controller, setting an X and Y, and then telling our drivetrain, since we used Mechanism this year, to move based on those X and Y coordinates and actually do something. And that's actually what controls the subsystem are these commands. So, and then whenever you're done with everything, you set the isFinished done. But since this is a command that should always be ran, finished is never done because we're in teleop. So,
okay.
I think that covers the basics of a command.
Sorry. So you were talking about how actually subsystems call on these commands. So I know we already covered drivetrain, but what other kinds of subsystems would we actually be using for our robot?
Alright, so another subsystem that is widely used would be vision, or should be used. It's a little bit more complicated, way more complicated actually. But you'll see our vision is quite complex in how many objects it has. There's a light relay, we have a camera, OpenCV is a very smart tool that we use, and so we use a sink and a source, a server to actually see our stuff. It gets really complex at times. We initialize our camera, doing different things. Then we actually have a thread. That is something completely different, but just think about two processes happening at the same time, at different speeds. That is what a thread is, so we have a separate thread going for our vision, so we can process that vision separately. And then based off of that stuff, we draw rectangles through the screen to see what the camera sees, filter down the image, stuff like that. And then that way, when we have this, we can use those values that it's calculated and use it inside of a command. So an example would probably be an approach peg. You see how we're requiring drivetrain and vision. And we don't really care about approaching, well, we do care about approaching in teleop. But what we're doing is we're taking that value from vision, so we have a vision.getCenterX, so the center value of both the rectangles this year. We get the center value of it from our vision, and then we do something based off of it. Some algorithm is ran against center X to figure out exactly what the robot needs to do, and then we set that, and then we tell the drivetrain to do something based on it.
Okay.
So that's a little bit more complex, but
Yeah, but thanks for talking about that because I think that's a very necessary part of the robot code that we actually use this year.
Yeah.
So we're coming up a little bit close to time. So I think that for any of my other questions, we should do another video, possibly in the
Sounds great.
future. But for now, thank you and goodbye, everybody.
Alright, thank you for watching. If you did like the video, please like and subscribe below. We do live stream around 6:30 Eastern Time every Sunday. We try to push about 3 videos in each live stream. So if you guys have any questions, let us know. Thank you guys for watching.